I'm going to switch between different modes, such as screen sharing and my document camera. I feel awkward speaking at this conference because I don't really have substantial results directly related to the H principle. Even though we have this Sergei Ivanov results on embeddings of Finsler manifolds, actually more or less complete theory, but it is not the H principle, to put it this way. I will try to say something about that. This is going to be probably naive and too elementary for real experts in this area. I would rather speak about other things. Let me experiment if I can switch to, well, maybe I just say it. I don't know. Maybe I'll try to switch to my digital camera. Well, not to switch too many times. What I want to do is to do some screen share, if that's different issue. And this is what I want to share with you. I don't know if you see that.
Yes.
This is Slava Kurylev. He was a very close friend of mine. He passed away about 2 years ago. This is a painting I did in his apartment in London. Last time I visited him, that was a personal visit. I came without no lecture, no anything. We had a bottle of white wine and some croissants together. And he was not supposed to drink any alcohol under medications, but he said, at this stage, I can do whatever I like to do. And he said that there is a project, and my will is that you can finish it, but can organize finishing that, because you're not so good in PDEs, which is absolutely true, but there are geometric stumbling points, which are the major problem, and you can organize a team. And indeed, I worked on geometric part. I even don't completely understand PDEs involved, understand algorithmics, but geometric estimates which were relevant, I started them with Slava and then continued with Sergei Ivanov, and this resulted in something I'm going to mention a little bit later. At that point, it seemed to be unrealistic. I think it is realized. What Slava said to me is that if it was done 20 years ago, probably they could save my life. It has applications to medicine, direct applications. I hope to be able to mention this, but I will start with very naive things, and maybe I'll try to switch to my digital camera. I'm sorry, this is going to be, this is, as it was said, the ending talk of the conference. Of course, everyone is tired, and I'm using very freestyle, and I'm going to talk about lots of little topics. So if at some point you feel you lose the line, no matter, in 2 minutes and switch to something else. If you want to have a nap, no problem. You wake up, I'm speaking about something else. If you need to take out dishes from your dishwasher, then okay, it's a relaxed talk. Works with you, I hope. As I'm taking advantage of the final talk. And especially also being not an expert. Now, not being an expert, let me try to switch to my digital camera. let's see if it's working. Probably just little notebook. Naive things which I'm asking from specialists, and don't know answers. I know unsatisfactory answers. Here is the first one to begin with. Of course, Nash embedding theorems, Nash, Gromov, whoever, by Gromov on partial differential equations, where differential equations are understood completely differently from how people in this area think about them. So it's a different area, but still, of course, let's take a torus. Let me see. T, some dimension n, don't care. Then I go to its universal cover, meaning that there is just an action of z to the n on this torus, right? And then I want to embed it. Of course, I can embed it due to Nash, Gromov, whoever worked on that, in some dimension into Euclidean space Rm. There is some dimension. Let me give it a name, Nash dimension, proper dimension. Certainly it is embedded, a classic theorem. But I want to embed it equivariantly so that z little n acts on this space Rm, well, in the standard theory. Can you do that?
Sorry, what is the standard way?
Just by translations, integer translations.
But on which coordinates?
Your choice.
So it's just embedding in torus cross Rn, basically?
Well, the issue is that I want to have exactly Nash dimension. The dimension here, it matters. If you allow me to increase the dimension, twice the dimension by Nash, I know how to do that. It is not written down, but this can be done. You want to have an embedding as a periodic surface sitting in this space, a periodic surface in this space, and this is periodic metric in rather general sense.
I'm sorry, I still don't understand the action.
The action is a subgroup of translations of Rm, which is z to z, which is isomorphic d to z, isometric translations of the group. So I want to see a periodic surface embedded. You can.
The universal cover, right?
Yeah, embedding the universal cover. This is not a compact manifold, of course. This is not compact. Call it M. It's not compact, right? I'm sending this thing. The torus itself, it can be embedded. I want to embed it as a surface so that we keep the action of the fundamental group by deck transformation, which acts on this universal curve, right? And we want this group to be sent to some Euclidean space where we embed it. as I said, if you increase the dimension, I believe I have an argument. But so far, I don't know how to do that with the same dimension. This is a question for.
But what exactly Nash dimension in this case is? What is it?
Well, Yasha, this is you by voice.
Yes.
I'm sorry. Okay, voice recognition.
Yeah,
Sorry.
that's me. Yes, yes.
Okay. You want to embed a two-dimensional manifold in some Euclidean space. What is the dimension? 5 is enough. 3-dimensional. Misha, you, many other people worked on improving the dimension. I'm calling it Nash dimension, whatever it is. Do we have to increase the dimension if we want to keep Z to the n action if the metric is periodic? If we increase dimension, there are easy tricks how you can do that. Can you embed it in the same dimension? With
So dimension, and it is a dimension in which you can embed torus just with.
yeah, it's a dimension of the ambient space, the space where we embed it.
Okay.
The torus is of given dimension. For a 3-dimensional torus, it's already okay for me. I would be okay. Yeah. I am formulating a problem. Kind of an answer which I can produce is absolutely not satisfactory for me, and guess not satisfactory for you. Yeah. Can you do it in the same dimension using classic technology, which is great, or some advances in that? And a question which is more or less related. I am indeed ashamed, awkward to say Yasha Leshberg, who is in the room, who is a great expert. I am an amateur in this area, right? So I'm sharing my naive thoughts for no reason. But say I want to embed the plane R2 into some Euclidean space. Sure, I can embed it trivially into R2 by just identity map. Yeah, but I want to send it to a region or whatever it is, which is bounded. Can you do that? What I can answer immediately at this point is that you can send it to R4 in a very easy way. What you do is you just take 2 copies of the plane. In each of them, you make 2 cycles. Then you make a spiral, winding and unwinding. Here is the same. Then the product. And then you are in R4. At least, can you send it to R3? And if it were not flat, even this construction does not work, at least directly. I'm not sure what you can do. Yes, in other aspects, I'm expecting some comments, meaning that you're an idiot and there is a ready answer for that.
I'm not an expert. You are an expert.
I'm definitely not. So where is an expert? I'm not, you're not, so who is an expert? Too bad. Okay, let me switch to something else then. A very naive question. I might know for myself, but not slides. Well, maybe I use some slides at some point. I don't know. A very naive question which I asked. I'm not going to dwell on it on a little bit long because then it's absolutely needed. Maybe I just show you some writing on that and you read it. You all can read. You have a trivial diffeomorphism. We started this with Vladimir Polterovich. Then the story went quite far away from that. You start with a trivial diffeomorphism of a two torus. And you want to, you measure how it's far away from the identity in two ways. One is how long is the path connecting it. The other one is just some CK norm. How to relate the two things together. With two graduate students, we did some progress in this direction, which is quite moderate. But for 2D, it gives at least some answer. Most likely, the answer in dimensions at least 4 or 5 is that you can't do anything. It should involve something quite non-trivial, like Nabutovsky thick knots or landscapes by Nabutovsky and Weinberg, or more advanced things, even in my opinion, by Fedor Manin. I cannot add anything. We did some triviality in dimension 2. It's open-ended. Okay. I'm jumping to something else.
But so what is known about this? Can you say?
If you well, there is an answer. If class of smoothness is k -1 instead of k +1, which I expect. The reason I expect k +1 because, say, if you think about one-dimensional problem, this is just integration, which increases smoothness by 1. In 2 dimensions, we lose smoothness by 1. This is what we can do. And only in 2 dimensions. In 3 dimensions, this mean curvature flow develops singularities and such, and this method doesn't work. I don't know.
Thank you.
If I don't explain things properly, re-ask me, I will slow down. I have just only 1 hour to talk to you guys. I'm trying to use as much as I can. Great opportunity for me. Another thing which is somewhat related, maybe to English problems, which I thought I would not speak at all, but one of the most useless results of mine, which, however, turned to be useful because it was also a topic of thesis work of a graduate student of mine who she proved a more useful result. You have a cylinder, Riemannian.
Can you just pull down the picture because you're
Yes. Thank you. Thank you. Yes. Sorry. Riemannian cylinder, and the integral of the curvature is less than infinity. Then you cannot embed it into a bounded domain. I spent several months on working on this problem. You cannot bend it into a bounded domain. There were partial results in this direction. Sorry to say that, by my dad and by Sheffield, who suggested this problem to me, and by Misha Gromov and so on. I have an answer. Now, the question which partially addressed by Sveta Krat, she was my graduate student, is you have a boundary. Near the boundary, you forget what happens. Otherwise, there is Nash, Kleiner, and so on approximation theorems, and which kill everything. You have a surface where the integral of its curvature is extremely small. Can you approximate it by a ruled surface? It's more or less a question about stability of the Monge-Ampere equation, right? If you rewrite it in PDE terms. She used my technology and developed it to prove that there is a reasonable approximation in C1, but not with the intrinsic metric. This stays as an open question. So you have a surface which is almost flat in the sense that its integral Gaussian curvature is close to zero. Is there a nearby solution of an honest equation where it is dead zero? Whatever it is, C1, you can find it. This is work by Sveta Krat. I was her advisor.
C1, but the embedding itself smooth C infinity, but just C1.
Yeah. Embedding is C infinity, of course. I want to, well, for me, it's C3 as differential geometry by training. C3 is enough for all relations, but assume C infinity. But closeness, that's what matters to me, right? Well, here is, let me see, maybe I have a slide to show, would be, maybe. Maybe I show you a part of this slide. Maybe a very small part. Let me start with talking. And here is more around mathematical literature than real mathematics. At some point, Slava, who I mentioned and who is, he inspired me in too many ways to even explain this here. At some point, he is Lassas, they invited me to a conference in Edinburgh on inverse problems in PDEs. Kalsman estimates and such, nothing of that I understood. Not much I understood even these days. Yeah, but they needed some story about Gromov-Hausdorff closeness for recovering images in those problems. So I gave a series of lectures, which then later were written down by another graduate student of mine, David Schoenthal, with my dad. I went to some lectures, not being too surprised, but with little understanding. And then, of course, my name appeared on a list of speakers in a conference about inverse problems. People started inviting me to such conferences. I couldn't say anything reasonable. I spoke about some geometry or such. And then there was a final conference of the year of inverse problems in Helsinki. And I was supposed to give their lecture and gave a lecture speaking about volume estimates in norm spaces. And someone asked me a root question, what does it have to do with inverse questions, with inverse problems, I'm sorry. And I answered immediately also the same style. I like root questions. I answered that study the equality estimate, maybe it gives you solutions. Then I came to St. Petersburg back and said to Sergey Ivanov, maybe we indeed tried to this approach. And we started working on those problems using this approach with some results. One of them even published in the Annals of Mathematics, another one in Duke journal. Some results were PDE approach, I mean, in 2 dimensions PDE because of conformal, Ullman and Pestov, they've done a fantastic work. I want to speak about something else, and this is what Slava Kurylev wanted me to organize. I can't say I've done that. I've done part of geometric part and some organizing work, but here is something I printed down on 2 slides. I will show the other one. This is a classic Gelfand inverse problem. It is known formally that it has a solution. However, for practical reasons, just the existence of solution is not helpful. The problem is, well, was thought to be ill-posed. And what we do is we show that it is not ill-posed. We can solve it. Now, what happens here? Maybe I say first what we started doing with Sergey Ivanov after this ruined lecture by me ruined Helsinki is you have boundary conditions, you have some region, you can't enter the region, but all you know is distances between boundary points. What can you recover about what is happening inside this region? Under some assumptions are obviously needed. Without assumptions, you can't do anything. With some assumptions, it turns out that at least if you know that it is not too far from being flat, then you can recover everything just from measurements of distances. Now, it is formulated geometrically. Of course, it is, in a sense, a PDE question because it's the same as you start with wave equations and look how long it takes for waves to travel from one point in the boundary to another. And it is done through some volume estimates in norm spaces. And then the question is really PDE, and this is Gelfand inverse problem. And now you can look at what I wrote down this night. You are given so applications which we hope for is medical imaging and say navigation of cyberknives, this technology. Machines exist, computer assistance is mediocre because I mean it's mathematically a non-trivial problem. We have some answers even in the form of algorithms. So here is what I want to show you, Gelfand's inverse problem. Let me move it properly, if I can. You have very little information. meaning that what you normally have, you have the boundary of a manifold. You don't know what is inside, but there are waves propagating through that, so you can look at the boundary and you can mathematically set up, look at eigenvalues of eigenfunctions, the standard thing PDE people do. And from that, you want to recover what is inside. So imagine ultrasound diagnostic or ultrasound navigation of a cyberknife to remove metastasis of cancer or anything like that. Yeah. And the thing is that indeed, it's 70 pages out of which I understand 40. There are complicated computations which are done by Mati Lassas and Jean Penglu and Sergei Ivanov. I only can check them formally. Geometric part, it's more transparent for me. You can do that, and there is even an algorithm. And here is what I wanted to show you next. What is done there? You can really recover what is inside in real time. Computational complexity is reasonable. So this is again where Gromov-Hausdorff distance comes up, even though you also can recover differential structure. By the way, I can share with you a very naive thing, which I use in my lectures for graduate students, of course, not for seminars, for serious seminars, but here I would risk that you ask yourself the following question. You have a differential manifold, and is it true that this is a quotient of just the topological disk? The answer is yes. Riemannian geometry gives you it immediately. You take a point, you look at the cut locus, you factor it out, you get a factor for this. Now, if it's just topological, there's a smooth structure. I asked this question a number of people. Eventually, John Rowe found a result which answers this question in positive with very non-trivial topology without smoothness assumption. Yes, indeed. And even topological manifold without smooth structure is a quotient for this. For topological manifold, I gave you a proof. Modular basic differential geometry. Okay, I sort of promised I would be jumping between topics, right? There's another.
Can I ask a question about the?
Absolutely. Questions welcome at any point, please. So
is there an effect of cloaking in this geometric problem? Can you hide stuff inside which you cannot see, like in the electromagnetic case?
Well, first of all, electromagnetic case is not Newtonian, right? It's a relativistic correction to Newtonian, but I'm going to make for you a little childish drawing, not the one I would prefer to do, a different one, because when I did it how I naturally would do it, I was speaking about it at Yale, and Bruce Kleiner, with a lot of sense of humor, asked me to erase it because it was obscene. So I'm making not an obscene drawing, thanks to Bruce. Here is a two-dimensional surface. Okay, here is a region. I'm not asking you to imagine what was the obscene drawing. It was just easier to draw. And then I'm thinking about how you connect points. And of course, no shortest path between boundary points would ever travel through this region. No, it is dead, right? So there is no way you can figure out what is here. No, right? So if you don't assume something reasonable, what is inside can be recovered. But there are standard conditions like simplicity of the metric, meaning that there are no conjugate points and boundaries convex. The latter one is not so important. In this situation, of course, no knowledge whatsoever, right? But it is more, if it is more or less like a disk, so that geodesic travels through more or less everything, you can learn better. Did I answer or more or less answer?
Perfectly clear.
Too bad. I mean, when something is clear in mathematics, there is no way out. Great academician Linik said to my mother the following thing: to give someone a clear problem is the same as to buy a new fashionable suit and say, now you take and wear it. Never give a problem. It's too big gift. Nothing is clear. And there are a lot of open questions here, of course. We have partial results. We hope to make some progress, especially if younger and smarter people join. Another thing which can easily be confused with something different, not trivial, but different. I will display the slide. I'm going to switch to, if I have time, probably I still am going to have some time. There was a fantastic feature of lectures by Vladimir Arnold. I attended some of them, and he speaks very fast. I mean, at the beginning, he speaks reasonably slowly, then he speeds up, speeds up, speeds up. Then you have a feeling that you understood everything. 10 minutes after the lecture, you realize that you have only a general feeling and can't recover anything. Still. I met him in person once when I spoke at the International Congress. I think Yasha spoke at this Congress at the same time, and also Leonid Polterovich. He approached me after my lecture and said, in a very familiar way, like if we were friends for a long time, even though I never met him and even never had a dream to meet such a fantastic, great person. And he said, we have common understanding. Sorry for a word. Mathematics is shit falling down on a rotating thing. And there is centrifugal acceleration. Anything goes with the rotation flies out. And only anything which goes against the natural direction stays there. These are words of Arnold said to me in person, the first since last time I spoke to him. Here is a story. In this story, there is a huge participation of Leonid Polterovich, who educated me, and Sergei Ivanov to some reasonable extent, not so good in, say, surgeries and symplectic geometry and Floer theory and such. This is, this sounds like dynamics, but this is just geometry. Here is the story starts with KM theory, theorem by Well. Again, I said this is a relaxing talk. At some point, I spoke to a mathematician, asked him what he's doing. He said, I'm proving a theorem by Misha Gromov. I put this in writing, and Misha approved that. At another point, I called Misha and said, you have a wrong theorem. He said, no, all my theorems are correct. I said, here's a counterexample. He said, you're not so stupid. This is not what I meant, just impose additional conditions. This is real mathematics. I'm praising Misha. He is a genius. So Kolmogorov's theorem, which was proven by ideas from Kolmogorov, by Moser and Arnold, and then many other people involved. And this is, if you have an integrable system, there is a classic Noether, Arnold, Liouville, whoever, theorem that if a homogeneous system in two n dimensions has n linearly independent integrals which commute, then it's integrable, and the dynamics is standard in the sense that everything is related by tori with standard motion, linear shift. You perturb it, then came theory says something absolutely fantastic and unexpected, that almost all of the space in the sense of measure is still related by such tori with quasi-periodic motion. What happens in the complement? And Kolmogorov asked, could there be hyperbolic dynamics, say positive measure entropy?
As someone who's also not an expert, could you explain what metric entropy is?
Okay. Of course, I can't explain it in the sense that it would take time. I can say some naive words, and this is a measure of exponential instability, commonly accepted measure of exponential stability. There are two more answers for that. I can try to give these answers. I don't think it's quite relevant to such a serious conference, but still, one answer is, if you assume smoothness, this is a theorem by Penn.
Again, pull down, please.
Oh, yes. Oh, yeah. Sorry. Thank you, Yasha. By Yasha Penn. And it says the following thing. You have smooth dynamics, so family of diffeomorphisms or flow, whatever it is, flow, FT, smooth manifold. And what you do is you look at the differential of the flow after time t. You look at its norm. Doesn't matter what metric you put on the manifold. You take its log. Doesn't matter what the base of the log is. You divide it by t. Of course, t goes to infinity. You look at the limit. You get what is called Lyapunov exponents. Strangely enough, they take just finitely many values at every point, psi I. You integrate them, you get the entropy. Entropy, measure of the flow. Okay, this is a theorem of Penn. Of course, the initial definition by Kolmogorov, Sinai, and many others is completely different. And if you want another definition, it would look more like that. You take space with a measure. You assume something. There is a measure. You take a partition. and you get information. So let's say it's in finite partition. You get information in which atom you know only the number I, where your point is. This is AI, okay? Now you iterate that. So time goes on, you apply your transformation, F now it's transformation, is a map from this space, let's say X to X, which is measure preserving, no, measure mu, whatever it is. And then you learn how much you know about this. Of course, after number of iterations, the partition, let's call it new. Next iteration is F new. Then it's F squared new. You keep going, F to some power over T new. You get a partition. Now for this partition, you measure the information. There is a commonly accepted way to measure this information. There is a minus sign to be okay. Sum of P of A log P of A. Measures of those days. Of course, sum of P of A's is equal to 1, total measure of the space. And you look how it grows. The exponential grows, so what you learn after the next iteration is entropy. In a periodic system, you learn almost nothing. In this exponential scale, you see nothing. In an Lassas system, so hyperbolic systems, you get some positive number for this thing. I understand this was not a proper explanation. I'm just trying to squeeze everything in. My time is almost running out, and I wanted to speak about discrete approximations to metric spaces, something completely different. Is this more or less okay, at least?
Yeah, that was great. Thanks.
Of course, it was not great, but anyways. So what happens there is what we do. I'm not going to explain what we do. It's quite a long paper, rather technical. And it is not about constructing a symplectic diffeomorphism with positive entropy if you don't care about dimension. Okay, geodetic flow on any negatively curved surface gives you such examples, and you can embed it somewhere symplectically. It's very easy. Of course, results of Berger to IF, Berger to IF are about something different. They're two-dimensional and show you twist maps with this property. This is not about this. This is how you realize such a map by perturbing Hamiltonian flow, by changing Hamiltonian. This is about what is about our work, and maybe in some wild sense, it is mildly related to the H principle. I don't know. It is connecting Lagrangian manifolds by some sort of analogs of geodesics in symplectic setup. This is what we've done. What we don't know how to do is what happens for a generic perturbation. Our perturbations are made by hands. We just prove that such perturbations do exist, even though you can destroy tori with quasi-periodic motion on them. In the complement, which is of course of microscopic measure, you can produce positive entropy, you can produce hyperbolic behavior on positive measure. Sheldon Newhouse showed you could do that on some Smale Shofu, which gives you topological entropy. Okay, here you can do it on positive measure. What happens in generic case, we have some ideas which are not realized. I probably have like 9 minutes or 8 minutes, right? Something like this.
Yes.
Something like that. Yeah.
Okay, I'll try to speak about a completely different problem. Maybe to inspire you to think about this. Let's say we start with a metric space. Okay. I want to do discrete approximation. In a number of years already, I'm always thinking about discrete approximation because any practical applications, they never work with continuous matters. Even if you have a continuous function, at the end you end with either Fourier series or Taylor series and some discrete set of numbers. So discrete approximations. So what you want to do, if you want to take a graph, for no reason, I put the vertices of the graph in the space. You don't have to do that. I put edges between vertices. And I want to have it tame in the sense that the degree is bounded by whatever it is. 3. 3 is enough for me. It is an epsilon net. What is epsilon net doesn't matter for me. It is delta separated, which doesn't matter to me what is delta. And for every edge, its length is bounded by 100, and whatever it is more than 1 over 100. 100 is a random number. I am taking this from early work of Dmitri Burago, who didn't want to care about constants and would put some fantastic, huge constants without worrying. Just saying that these constants would work like e to the power, e to the power 1,000 to the power whatever they were. So 100 and 1 over 100, they are relevant. So what I want to do, this is a graph gamma. Okay, this is a metric space X. You have X with a metric D. You have gamma, it has its metric D of the graph gamma. I want to approximate my metric space by this graph, meaning that I want to have some constant, C, any constant, but a number.
Sorry, is this a combinatorics problem?
It is a geometric problem. It is not
Just
combinatorics. No, it's geometric. In the remaining 5 minutes, you will see it's purely geometric. I mean, combinatorics is very little involved there. There would be some Fourier series and such, and some functional analysis, and combinatorics plays very little role. But what I want to do is that the distance between any 2 points in X differs from the distance in the graph by no more than this constant. So I want to approximate the thing by an additive error. Can I do that? With Sergei Ivanov, we spent a lot of time on this problem, and we have partial answers and very bad questions. So partial answers are as follows. First of all, I want to assume
Could you put down the paper, please?
Yeah. Oh, yeah, I'm making this mistake all the time. Bounded geometry. Wait a second, I will put it down. I'm more used to draw on an easel than on a piece of paper. Yeah. So assume bounded geometry, whatever it is, injectivity radius, curvature. Yeah, because if you don't assume that, of course you can't approximate even very simple things. You take a tree, it branches, then it branches again. All lengths are equal to 1. Then you take a tubular neighborhood of this tree, which gets thinner and thinner. And of course, there is no way of approximating by a graph because the degree is supposed to be bounded, okay? But with bounded geometry. And the question which remains totally open, and I will just write it down. Does there exist a manifold of bounded geometry which cannot be approximated by boundary graphs? I put in quotation marks.
Now we don't see the lower half.
Yeah, I'm going to list that. I need to write. Yeah. Does there exist a space of bounded geometry? So from now on, bounded geometry is a standing assumption. Now, theorems which we have. One of them, surprisingly, takes more than 10 pages of proof with analysis and so on, is that R2 is approximable. And this is about what I want to speak for maybe a minute. Another statement is that, so this is one statement, that another statement is Gromov hyperbolic and bounded geometry, as I said, it's standing assumption, is approximable. This is much easier, strangely enough. Even for R3,
Is the first or the second much easier because we don't see the top, the second? Okay, thank you.
R2 is approximable, the plane. For R3, we can't prove that. And we have even not at all an example of a space with bounded geometry, which is not approximable. I mean, for which we cannot show it is not approximable. This is an open question. Now, if you think about R2, I'll try to be as much concise. First of all, non-example. Never try to take a graph like that, because what you get from this, the grid, Manhattan metric, would give you L1 or L1, whatever it is, metric. I mean, it's linearly different from Euclidean. You want to have L2, right? Whatever it is. Now, any periodic graph doesn't work. It's an exercise for a reasonable graduate student, because if you take any periodic graph, if you look at large scale behavior, what it would give to you is going to be a polyhedral, polygonal, and two-dimensional norm, which is not nearly Euclidean. So nothing periodic works. Things should move something in a strange way. And we make them move in a strange way. We can do that in 2 dimensions. And here is the last thing I'm going to say, is you have an interval on 0, 1. You have a function f. Assume anything you want from it, reasonable, non-negative. Let's say it's convex or concave, whatever it is. C2, boundary conditions, reasonable. And what you want to do? You want to approximate it by the sum of distances from A, I, to X. 。 Now, these points AI are from the interval. You average them by m, sum from 1 to n, and you want to approximate it to these functions. Surprising answer is that you can approximate it with fantastically good precision. So these are absolute values. You cannot, these are classic results of Roth and Schmidt and so on. You cannot uniformly distribute these points AI on the interval. However, if you take absolute values, even if you look at this sum, now I'm not going to divide. I'm putting the same sum, distances from AI to x minus f times n. This is sum from 1 to n. You can make it less than 2. This is the key point in the two-dimensional case. For higher dimensions, we can do anything. So even for equal distribution, so you see enough points in every interval, classic theory says you can do that. There are some log time restrictions. However, if you even not smoothen it, but you just use absolute values, you can do that. In higher dimensions, this is totally open. I'm finished, even a couple of minutes over my time. Sorry.
Thank you, Dmitri. Are there questions?
What is this approximation of R2 look like?
It is kind of strange. If you start building a periodic graph, anything periodic, you can start anything. And you look at its asymptotic behavior, it's not a circle. It's asymptotically it is. You see a polygonal norm. Now you start changing this thing somehow, non-periodically, of course, but a little bit. This thing rotates. Here is by absolute values. This is what I wrote at some point. Distance from x to AI. These are more or less geometrically shapes of this polygon. They rotate, and you work on cancellations. Cancellations of errors, which you make, so that they become bounded. And for that, what we used was very easy. I mean, even undergraduate, graduate level Fourier analysis. Well, even not analysis. I'm serious.
Do you have some useful literature on this? Because I'm familiar with like different variations of this problem.
This paper, I think, is already published in GAFA. Developments, say, we are working with Chen on paraboloid and the sphere case. Of course, sphere is bounded space, but you can look at spheres of different radii and ask for approximation with the same error. This work is published.
Okay.
Developments are not. Things are in progress.
It's a great talk, thanks.
Could you go back to your second question? I mean, the one on R, I mean, in which you asked whether you can put R2 inside a bounded set of the three-dimensional Euclidean space.
Yeah, it's just that.
Yeah, but what regularity do you want on the?
I want to take R2.
Yeah.
Which is Euclidean metric.
Yeah, that I understand.
I want to send it isometrically.
Yeah.
And embed.
Yeah, that I understand. But how regular do you want the map?
I want it to be at least C3, but C infinity. No, I don't want to see Nash Cooper examples of Ivan flexibility. No, it's I want to at least C3. Then geometry survives.
But I mean, if you have an
I want it to
isometric
be C3.
embedding, if you have an isometric embedding of R2 into R3 and it is C3, it is a ruled surface.
Well, but then you lose smoothness. Again, I said Nash.
No. I mean, a smooth embedding of R2 into R3 is always a ruled surface. It's a classical theorem, right?
Okay.
I mean, any small flat piece that you are actually embedding into, which is flat, which you're embedding into R3, is going to be a ruled surface, no?
You see what I wrote?
Yeah. Okay.
And this means.
Okay.
Yeah, indeed, it's a ruled surface, so it never could be. Yeah,
It never can be in compact set.
yeah, it's ruled, so answers the question.
Okay.
Yeah, it's an exercise. I even give it to my grad students in my Romanian geometry class. Yes, any embedding of well, it's ruled. Furthermore, if it is a whole plane, it's a cylinder over some curve.
Yeah.
It's an example. So R3 doesn't work. I am working from R3 to R proper dimension. Yeah, this comment kills the question in this dimension. Yeah, but see, R2 to R4 you easily embed it.
Yeah. That was clear to me.
Oh, this is a triviality.
Okay, another question? Well, let us thank Dmitri again.
Thank you very much for attending my